Our speaker next is Otto Lang. He is a PhD candidate with the University of Utah, so please give him your attention.
All right, hello everyone. It's an honor to be here talking about my favorite topic, which has also consumed a lot of my life in the last 3 years in a very good way. My name is Otto Lang. I'm a PhD student at the University of Utah, and I'm going to be talking about quantifying the impact of dust on snowmelt here in the Great Salt Lake Basin. Before getting started, I really want to thank my advisor, Mackenzie Skiles. She really kind of pioneered a lot of the motivation and the funding for this work, as well as all of the collaborators and coworkers kind of up and down the Wasatch Front and around the Rocky Mountains that have really contributed to this work, both in terms of data and in terms of ideas. So jumping in, the area I'm going to be focusing on is really familiar to all of us here. It's the snowpack of the Great Salt Lake Basin. And specifically, I'm going to be focusing on the 3 primary watersheds that contribute surface water inflow into the Great Salt Lake, right? The main one being the Bear River watershed, the Weber River watershed, and then the Jordan, Provo, Utah Lake River watershed as one. We all know that living in the Wasatch Front, right, our snowpack is a huge source for water, and it really drives our economy, not only in municipal regions, but also for agriculture and rangeland. And the snowpack is our largest natural reservoir, right? So it's really important to understand the timing of snowmelt and the rates of snowmelt and how that impacts stream flow forecasts and potentially reservoir management going forward. So before talking about some of the detailed work and some of the dust on snow processes, I just want to give a really quick overview on how snow actually melts. I think most of us, when we think of snowmelt, right, we think of air temperature. But one of the main contributing factors to snowmelt is actually solar radiation. This is sunlight, the sun's energy coming down. Snow is really bright, reflective normally, especially when it's clean. So a lot of that radiation is actually being reflected back out. But despite that, the snow is still absorbing a ton of energy from the sun itself. So in addition to that, we have, of course, air temperature that contributes to snowmelt. We call this sensible heat. We have basically phase changes, condensation, evaporation. All those can contribute melt to the snowpack. And then we have this term called long wave radiation. This is coming from things like clouds and trees. This can also melt snow. But once again, the purpose of this talk here in our mid-latitude, generally sunnier snowpacks, it's really our solar radiation, or the amount of sunlight we're getting onto the snow, the amount of sunlight that's absorbed into the snowpack itself. This is what's going to be controlling our snowmelt. So let's imagine, right, we have a completely clean snowpack. It's a beautiful day. There's nothing darkening the snowpack right now. We just got a fresh snowfall out in the mountains. Most of that incoming solar radiation, about 90% of the visible wavelengths are going to be reflected back out. So the snow itself isn't actually going to absorb a ton. This bright snowpack will generally result in pretty minimal melting, especially in the winter months. However, if we get dust here in the Wasatch and the Great Salt Lake Basin, right, most of our dust comes from the West Desert regions, the Great Salt Lake Desert, the severe dry lake, as well as the lakebed of the Great Salt Lake. If any of that dust lands on the snowpack and is exposed on the snow surface itself, right, that darkens the actual snow surface. It causes it to absorb more energy. The same way wearing a black shirt on a sunny day, right, feels warmer than wearing a light shirt on a sunny day. That darker snowpack is going to drive melting. This causes essentially the snow to disappear earlier than it would if we didn't have a darkened snowpack, and also accelerates melt. This generally increases the uncertainty in predicting the timing and magnitude of spring runoff unless we account for how dark the snow is as well. So as scientists, the way we think of this in terms of a quantifiable metric, right, is this term called snow albedo. This is essentially the reflectance of solar radiation. So higher values, right, this ranges from 0 to 1. Values such as 0.9 are going to represent pretty clean, bright snow. Values such as 0.5, right, this is where 50% of the energy is actually absorbed into the snowpack. This is going to represent pretty dusty, dirty snow. So this brings me to my overall research question, right? How does dust here in the Great Salt Lake Basin actually impact snowmelt rate and timing? So we took a three-tiered approach to answer this question. First, we focused in on one point, and we're like, okay, let's conduct a field campaign over one season at one study plot to figure out, okay, what are the kind of the detailed processes going on here with the goal of understanding these impacts at one point using mostly field measurements. Expanding from there, we used satellite observations. Satellite observations going back almost 2 decades, since about 2001, to try and understand how has dust on snow changed in the Great Salt Lake Basin over the last 20 years. Have we been getting more dust on the snow surface? Have we been getting less? Is there a pattern we can use to predict dust on snow in the future? And then lastly, our goal here is to really understand how does this translate to snowmelt? How does this actually shift our snowmelt timing? And this is where we're ingesting these satellite observations directly into models to understand the spatial impacts that this snowmelt has across the entire Bear, Weaver, and Jordan River watersheds. So the first part of this talk is going to be focused on at-water study plot. And if you're not familiar with this study plot, it's in the town of Otto, Utah, the top of Little Cottonwood Canyon. It's directly across from Otto ski area. And here, we started our field measurements in the 2022 water year. So this is the 2021-2022 season. We really did an in-depth investigation of snow parameters, right? We dug snow pits, we measured snow depth, density, stratigraphy, as well as sampling individual dust layers as they were deposited on the snowpack. In addition to that, right, we have a tower at the study site, and on this tower we have meteorological instrumentation that measure all the parameters that control snowmelt itself. We have solar radiation being measured, both incoming and reflected off the snow surface. We have long-wave radiation data. We have temperature, wind speed, humidity, and a variety of other factors. So how do we take all these data and actually quantify the snowmelt impact over one season at the site? So what we did is we used a modeling approach. And this model is forced almost entirely with data we observed in the field. So we take data from our instruments, such as wind speed, temperature, the amount of sunlight we're getting. We're plugging that into the model. We have our initial conditions, how deep the snow is, how dense the snow is. We plug that into the model. And that basically gives us our observed melting conditions. We compare that to a scenario where we're using the same model, but the only thing we've changed here is the actual snow albedo, or the reflectance parameter of the snow, and we've changed that to represent a clean snow, so really high reflectance. So then we can look at the difference between those two models. So here on the y-axis, I have snow water equivalent, right? The amount of water stored in our snowpack. On the x-axis, I have, this is dates, and this is for 2022, so starting in April, going into June. The blue here represents actual field observations. This is when I and my colleagues, we went out in the snow pit, we dug a snow pit, we measured the amount of snow water equivalent at the snowpack. The bars here represent the spread of snow water equivalent across our study site. And the brown line here, this is our model run, the outputs of our model run using those that field data from the tower itself. We see that generally it closely tracks our observed snow pit conditions. The green line here shows us the model run where we kept everything the same, but we changed the reflectance of the snow itself to represent a hypothetical clean snowpack. And you can see that it generally melts 17 days later, or another way of looking at this is the dust and all the other dark particles on the snow shifted snowmelt about 17 days earlier. So this is great information, but it's for one season at one study site, right? So it doesn't tell us a lot about long-term trends or the spatial variability that this dust has. So this brings me to the next part of my talk. Is here we're using observations from space to understand how has dust on snow changed going back at least 20 years. So if you don't like math, just close your eyes for 30 seconds. But bear with me, I'll try to keep it as simple as I can. The way we detect dust on snow from space is we use the sensor called MODIS. MODIS is mounted on 2 satellites, and we get retrievals every day. So we get essentially a reflectance measurement of the snow surface everywhere in the Great Salt Lake Basin once a day. We essentially use the same approach where that satellite, let's say it's flying overhead. This is our hypothetical snowpack, right? We have a dust layer exposed. It's at the top of the snow surface. The satellite is reading an albedo of, let's say, about 0.52. The algorithm then compares that to what it thinks a clean snow albedo is. This gives us our snow darkening term. This is a way we basically get at how much dust is on the snowpack. And then that's multiplied by actually the amount of sunlight reaching that location at that time in order to translate that into how much actual energy is absorbed into the snowpack because of that darkening of the snow itself. So this term, right, this is called dust radiative forcing. Again, this represents the amount of energy absorbed in the snowpack due to dust. We get these retrievals daily. So here we just have a kind of a satellite image from Sentinel showing us the snow cover. This is in June. And then here is a typical example of one of these retrievals, right, where we have these relatively coarse 500 meter by 500 meter pixels that are showing us, okay, how much has darkened snow impacted melt. And since we have these data, right, every day for the last 23 years, this gives us a great opportunity to actually look at trends both spatially and temporally of how has this dust snowmelt impact changed over time. So for the next couple slides, on the y-axis on these plots are going to be that radiative forcing value. You can think of this again as just a greater snowmelt impact that these darkened particles are going to have. And now this is averaged over the full record. So this is 23 years of data over the snowmelt period, which I'm defining here as April through June. And you see that as we kind of progress through snowmelt, that the impact of dust, right, generally increases exponentially over our snowmelt season as we're getting more stuff landing onto our snowpack and as we're getting more sunlight into the summer months. If we look at some of the spatial averages across the Great Salt Lake Basin, right, this is average over the whole record again, we see that there's actually not a statistically significant difference between the basins, but generally we have higher dust impact years in the Jordan River watershed, and less so to the north. So let's take a look at some of the actual years in this record, just as an example. So we're going to go all the way back to 2009 because this was really kind of a year that had a lot of dust impact on snowmelt. And the reason for this is that we didn't just have a lot of dust during this year, but that dust was actually exposed on the surface for quite a long time. So again, in this plot here, I'm showing the same thing, right? We have a greater snowmelt impact on the y-axis. We have time over the snowmelt season on the x-axis again. The only difference here is I'm showing everything from an average for that time of day. So everything above that black line is going to basically be dust or darkened. Any darkened snow is going to have above average impact. Everything below is going to have below average impact for that day compared to the record. So what we see in 2009, we really had this really prolonged period of dust exposure throughout all basins in the Great Salt Lake Basin. And that's because we got a lot of dust here. On the right is an image of, you can see individual dust layers in the snowpack, but what's important here is that those dust layers were also exposed on the surface, and as they combined, they really accelerated melt in this year. And one other thing I'll point out is that the coloring here, this is colored by watershed. The Jordan River is blue, the Bear River is yellow, and the Weber River watershed is red. So this is an example of when dust had a lot of impact on melt. If we look at kind of an opposite scenario, this is 2015, which was a really low snow year, but it was also a low year in terms of the amount of dust we got on our snowpack. Despite it being a low snow year, it actually ended up being somewhat snowy in the spring of this year during the snowmelt season. So we see, here's an image I pulled, right? This is late May, that we've basically had pretty minimal dust exposure. And that shows up in the satellite record as well as pretty below average dust influencing snowmelt during this time. Now those are kind of 2 years that have a pretty good consistent story, right? And when the reality is, here in the Wasatch especially, we get a lot of snowfall as well as a lot of dust in a lot of years, that these kind of differences or this melt impact becomes much more difficult to parse out. 2022 is a perfect example of this. Here is a snow pit picture on the right where we can see we got a ton of dust deposited in our snowpack. From our field measurements, this was the most dust we've ever had in terms of concentration in a snowpack at our study site. But if we look at the remote sensing record, we see that generally it's kind of variable, and it also varies between watershed, how much that dust actually impacted melt. And a lot of that is because we had a lot of dust in our snowpack, right? But we also had a lot of snowfall that was burying those dust layers, resulting in generally minimal exposure. Therefore, the impact is kind of around average for this year. So the final thing I'm going to show before moving on to the last part of my talk is the full record from these satellite retrievals. So this is starting in 2001 here on the x-axis, going all the way to 2023. Again, this is our radiative forcing anomaly or difference from an average value. We can think of greater snowmelt impact again being kind of increasing up on the y-axis. So this record, when we first quantified this, was somewhat surprising to us because there's not really an increasing trend over time. There's not really a decreasing trend. And there's no real definite cyclical pattern here that would enable us to predict whether the next year is going to have above or below average impact, that dust is going to have above or below average impact on snowmelt. We do notice we have a lot of high interannual variability, right? We have these years where we get a lot of dust exposure, followed by years, well, where we get practically or very little dust exposure. And this basically, there's no like consistent pattern here throughout the record, so we see that interannual variability is really the main driver here. There's one thing to note, if you've been around the Wasatch for a while, you've probably noticed that the last few years have felt dustier. If you've been in the snow, have felt dirtier than the years preceding that. And that does show up in our remote sensing record, right, that we're kind of coming off this period of average to below average dust impact. However, we don't have this long-term increasing trend over the whole record. And the last thing I'll say here is that these are differences from average. Every single year in our remote sensing record had a pretty substantial dust impact overall. So really dust on snow in the Wasatch and in the Great Salt Lake Basin is really part of the snowmelt story. It's normal and it happens every year. So now we've looked at how dust on snow has changed over the years, right? How that's expressed in snowmelt, but how have these snow darkening retrievals actually, how do they express themselves in terms of snowmelt timing, right? How is the snowmelt timing variable over the Great Salt Lake Basin? What aspects, what elevations are most impacted by dust on snow? This is kind of the point of this third part of my talk. So the methodology we used here is really similar to the first part of my talk, if you remember. We're using a similar modeling framework. These are physically based snowmelt models. Again, we're running a condition with, or we're running the model with observed conditions, but since we're running everything over the whole Great Salt Lake Basin here, we can't rely completely on field data because we don't have field data at every pixel for the model. So instead, we're using model inputs from the HER numerical prediction weather model. So this gives us things like precipitation, wind speed, solar radiation. All of that's coming from a weather model. It's plugged into the observed conditions run. And then again, we use our satellite retrievals that are detecting the reflectance of the snow and ingesting that into the model. Again, we compare that to a model scenario where everything is held the same except for we're not taking these satellite retrievals of the actual snow albedo. We're assuming that the snow here is clean, dust-free, and has relatively high, really reflective snow albedos. Both of these model runs output snow parameters such as snow depth, SWE, all the components that go into snow energy balance at 100 meter by 100 meter grid over the whole Great Salt Lake Basin. And we've done this for the water year 2022. We're working on 2023 over all three basins. So before jumping into some of the modeled results here, I just wanted to show some actual field observations for this season. Again, we're focusing here on the water year 2022 and the Jordan River watershed, because that's where we are in 2022, so we can compare directly to the first part of my talk. where that was the year of focus. So here on these plots, I have snow depth on the y-axis, and then time on the x-axis, starting, this is a full water year, so we're starting in October, going all the way through the end of September. And here in the Jordan River watershed, we're really lucky to have a really dense network of snow observation sites. We have 17 snowtail sites for this water year in this basin, so we can actually look at the observed snow depth at these sites, at the general aspect and elevations of these sites in terms of a median and then a spread, a percentile range. So then we can run the model. Here I'm showing the model run with a clean snow scenario. We can look at the values at the pixels where these snowtail sites are, and these are the results we get. So here, if we run the model assuming hypothetical, clean, beautiful, pristine snowpack, we see that it kind of behaves as we would expect, right? We get kind of snow depth that's a little bit too high, and we get generally our snowpack melts out much later than it does in reality, and that's because snow is essentially never just purely clean, and usually has some sort of light absorbing impurities in it, like dust. So if we look at our model run where we're actually directly ingesting the observed snow albedo parameters, we see that it much better tracks the kind of range or the median of the snowtail sites. Again, this is the model results at the pixel values of these snowtail sites. We see that when we include the darkening impacts by dust, right, we get a much more realistic approximation of snowmelt. You can see that the shift between the snowtail date here and the modeled with dust run is only about 6 days as opposed to almost a month to the clean snow run. I will say that our model does tend to melt snow a bit faster than reality still, but we're kind of working on improving that. So this is really cool because now we have a metric, right? If we look at the shifts in snow depletion date, right, this basically allows us to quantify the impact that all light absorbing impurities are having on snowmelt. This is going to be primarily dust in this region, but it's also the cumulative impact over the whole water year. So we're starting here in October, right? This represents all of the darkened snow that's landed on the snow surface since October all the way until the snow melts. So we see that these shifts are actually quite substantial, and that the snowpack has a lot of dust in a given year, especially in this year, and a lot of other particles that are actually contributing significantly to the snowmelt. So now that we have this metric, right, this shift between clean snow and dusty snow in terms of melt depletion date, how does this actually change spatially over aspect, over elevation? So here is my way of showing this, and this is essentially a rose diagram plot. You can think of this as looking top down onto a mountain, right, where the values in the center are going to represent higher elevations. The rings on the outside represent lower elevations, valley floor elevations. And then the aspect or the direction these slopes are facing are given kind of in the compass directions around the outside here. So the values I'm plotting here, this is the shift in snow depletion date or snow disappearance date between the different model runs. So you can think of this is the impact dust had on this particular aspect and elevation. And this is again for the Jordan River watershed in 2022. So there's some interesting trends we see in this data. So let's go through it. If we look at just the alpine areas, this is generally above 10,000 feet here in the Wasatch Mountains, right? We see that the shift is pretty minimal, maybe on the order of 5, 10, 15, maybe days. This is because even if we're getting a lot of dust in these areas, the dust is pretty infrequently exposed, right? We're getting a lot of snowfall even late into the melt season. So generally clean snow kind of dominates the melting in these regions a lot of the time. Stepping down into the more subalpine regions, right, we see this is where darkened snow really has the greatest impact in actually changing how snow melts and the timing which snow melt occurs. Here we see that, and the main process behind this is probably that it's pretty simple, right? Snow begins to melt generally earlier in the alpine. We have more dust exposed. We get less snowfall in the spring months, especially as we get closer to June. So therefore, dust is having a greater impact on these, in these elevations. And then lastly, if we look at kind of the southerly half of the compass, we see that dust on snow has a greater impact on these sunnier slopes. And that makes sense because if you think of a nice sunny slope, more sunlight is hitting that slope. That gives the dark particles more available energy to absorb, therefore having a greater snowmelt impact. So just to summarize here, right, we really see our southerly mid-elevation slopes being most sensitive to changes in melt timing because of dust deposition. Last thing I'll say here is that these patterns, right, we see them not only for the Jordan River watershed, they're pretty consistent across all of the basins we looked at, the Weber, as well as the Bear River watershed. So I'm just going to wrap up here with a couple of take-home points. The first being that dust on snow is normal in the Great Salt Lake Basin, at least since our remote sensing record that we used began in 2001. We really show that the snow darkening impact is present every year. It's only the magnitude of that impact that varies quite a bit year to year. We also see that there's no robust multi-decade trend that allows us to predict that impact based just off this record alone. Secondly, it's not just the amount of dust that lands on the snow that actually matters. Exposure is really important here. You can get dust that lands on the snow, gets buried by a ton of additional snowfall, and that's really not going to have a large impact in terms of snowmelt. Here, the meteorology of a given spring, the frequency of snowfall, and the timing of dust events is going to really contribute to how dust will influence melt in a given year. And then dust, the impact of dust on snow, right, it varies by terrain. It's generally the greatest where it's exposed the longest. And here in the Great Salt Lake Basin, there happens to be southerly aspects at subalpine elevations. And the last thing I'll say here, which is really exciting, is that I've essentially said that it's difficult to quantify or difficult to predict whether a given year will have a higher or lower impact in dust on snow. But we have this approach now, this modeling approach, in which we use the observed snow reflectance either from the field or from satellites, and we can much better, more realistically predict snowmelt in real time. And thank you, and I'll take any questions.
Thanks, Otto. We have a good amount of time here for questions still. We'll have a few mics going around, so just raise a hand and we'll come over to you.
Thanks, Otto. It was a great talk. So for your snow melt output, I noticed it was plotted in snow depth. Does the model also output snow water equivalent? And can you talk a little bit about the differences in those two metrics?
Yes, definitely. It does output, it outputs snow density and snow depth, and then you can do the calculation to calculate snow water equivalent. Obviously, the melt depletion timing is going to be the same as snow depth, and a lot of the patterns are similar as well. The model does, at least in the Jordan River watershed, tend to underestimate snow water equivalent a little bit more than snow depth.
I was curious about sort of the mechanisms of the melting process. So if you have like a dark layer of particulate matter accumulation, do those kind of accelerate the melting of the snow as the season goes on? Like, do those layers kind of stack as different sort of strata melt?
Yes, that's a great question. So when we get a dust event and the dust lands on the snow, usually that dust is exposed relatively near the surface, right? But if you do have snow above it, as that snow melts, that water will leave the snowpack, but the dust particles and the other darker stuff, that will actually stay near the surface. So what happens if you have multiple dust layers in your snowpack, as melt progresses, those dust layers will kind of emerge at the surface and they will actually combine. So you get this accelerated impact as the dust essentially concentrates on the surface as you're going through the melt season. Yeah.
Yeah, a great talk. Do you know, or could you speculate on why the Jordan watershed was a little bit higher? Was it, slope aspect or elevation, or was it maybe the dust sources?
So there's nothing that shows it's like statistically higher, but it does seem to be at least, always on the higher end. If I had to guess, I would guess proximity to dust sources. and in closer proximity to like southern dust sources, such as like the southern Great Salt Lake Desert, the Severe Dry Lake, things like that. Yeah.
Hey, thanks for your presentation. My question is about kind of going forward, looking at climate models into the future. Is there anything that shows more longer interstorm durations? Because it seems like that would be the times when the dust would be the most negatively impacting the melt-off.
That's a great question. What controls kind of the patterns we see? That's very like ongoing work, and I wish I had a better answer, but that, you know, the changing frequency of storms and the changing intensity of storms is going to have probably a large impact on the patterns we see. Yeah.
Did the record-setting 2023 snowpack impact your fieldwork at all or complicate it?
Yes, it did. I didn't throw any, digging the snow pits was quite challenging, definitely when the snow is 15, 16 feet deep. And it actually almost buried our instrument tower itself. We had to actually mount the sensors higher, and some of the instrumentation got fully buried. But we were still able to collect everything we needed to run the model.
Thank you so much. I'm wondering if you've seen any patterns as to when like a high frequency of these dust events happen, whether it's in March or April, or varies from year to year.
Yeah, it definitely varies from year to year. I'd say April is probably the most common in terms of the frequency of dust events we get, and the frequency of dust events that actually impact snow melt, I should say.
Hey, thank you. Awesome talk. I was wondering if you had any kind of preliminary ideas for why you're seeing the discrepancy between the observed snowmelt data and your model, just for
Yeah, the
improving
6
in the
days
future.
there between the snowtel.
Yeah, just any differences that are between those two.
Yeah, I mean, the first thing I'll say, it's not a direct comparison, right? Snowtel sites are at one point, and our model is a 100 meter by 100 meter pixel over that area. Snow depth can vary a lot, you know, even in just like a space of 100 meters. And also, our model has a ton of inputs, so things like the amount of precipitation that's input in a given storm compared to reality can be a little different sometimes. The actual like albedo values, you know, they're probably not perfect. So there's definitely a lot of factors that play into there.
Cool. Thank you.
Thanks. Thanks. Great talk. I want to make sure I understand something that has come up in a couple of the other questions. So it's the accumulated amount of dust, but it's also where it is in the snowpack. And I think I've observed this just in the field, but as the snow melts, the dust tends to stay on top. So for example, if you had a huge dust event in November, but it was then varied, even though it wouldn't have much effect until the snow melted out to that level. But even if you had a couple of minor dust events, say in late May, as the snow melted, that would accelerate the entire snowpack. Is that correct?
That's completely
Okay.
correct.
And then I also I'm just curious, have you seen, is there any work done on the type of dust? Because that's basically, I mean, it's particulate that comes out of the air, but is there a difference between some of the heavy metals that we're concerned about now in the dust, or just the dirt, or perhaps dust from a concrete quarry? I'm just curious if you've have any information on how things like that impact it.
Yeah, I myself haven't looked on like the actual parsing out the chemistry of the dust or anything like that. We've done some atmospheric back trajectory modeling work with some colleagues that have basically looked at some potential dust sources. And those all indicate that generally the West Desert, the mineral dust coming from these kind of playa regions, that's really what's dominating the amount of like mass we get in terms of our, that's actually in the dust. There's some chemistry data you can like, I haven't done this, but Greg Carling at BYU has used strontium isotopes, measured those in the dust to actually kind of trace back kind of which playa they may originate from as well. Yeah, so I mean, we parse out kind of how much of it is like mineral dust, like minerals, versus how much of it's actually kind of like contributions from pollution, like black carbon. And generally, we see that it's really the mineral dust that's, and from the papers I've read, it seems like that chemistry of the dust seems to be consistent with these kind of desert playa sources that we get in like western Utah.
Hi, awesome talk. I had a question. So you mentioned that dust was a part of the story here for snowmelt in Utah, but you didn't mention that there was like a 5 or so year span of much more dirtier snow. And I was curious if those were preceded by like drought events or large fires in the summer that would have basically like foreshadowed their coming. Is there any general trends that we see for a dustier year than another non-dustier year?
I wish there were easier trends, definitely. I've like looked at it. It's interesting because we see this period of kind of below average dust impact from 2015 through 2021, and that actually coincides with kind of lots of years of drought during that time. So you'd almost expect the opposite for drought to have, you'd expect more dust, right? You'd expect more dust landing on the snow. But what we've learned is that it's generally relatively complicated. My guess would be that the frequency of storms, a lot of our dust comes right before we get a major winter storm that brings dust, but also brings snowfall that buries the dust. So a lot of these factors that are important in understanding the trends actually kind of pull both ways and can be very like case by case specific.
Thanks for your talk, Otto. Can you briefly highlight how these results that you've shown can be implemented into water supply forecasting and the outputs from these data that you've collected?
Yeah, definitely. So that's kind of the overarching goal of this work, right, is to improve our modeling capabilities for snowmelt modeling, right? Not running these models that are based off air temperature, but actually running these models used here, which are physically based. They essentially have all the physics built in them that actually controls snowmelt. And so what we've shown is that we can use our observations, right? We can take these incoming satellite observations that we're getting every day, and we can use them directly into these models to better predict snowmelt.
I understand that also in like high alpine regions, there's algae that later on in the year can affect like the coloration of the snow and whatnot, you know, often turning it pink. And I was curious how much that affects the albedo and if the dust could potentially affect those populations of algae if it provided more nutrients and affected, you know, how much those also effectively influence the albedo of the snow.
That's a good question. I'm not an algae expert, so I don't exactly know. I'm not super familiar with like the dynamics between the nutrient cycling that causes the algae growth. I will say that when we're talking about like the retrievals from the satellite, it's measuring this reflectance of the snow and how dark it is. And that includes dust, but it also includes anything else there, like snow algae at that point. So we're essentially, when I'm showing these results as, you know, kind of the darkened snow versus the clean snow, the darkened snow in a given location is gonna be dust, algae, leaf litter, anything else that's on the snowpack making it darker. So we, using this approach, can't really parse out, you know, how much algae is contributing to melt here, but it's definitely, at least from what I've seen in the field, it definitely kind of blooms later in the season, like in June when you get a lot of sunlight. So it's definitely influencing melt there. But I don't have a good answer as to like how much that is compared to dust, but it's probably pretty minimal compared to dust. Yeah.
Okay, we have time for about 2 more questions, and then it will be time for everyone to go to lunch after that.
Do you see much variability in your data from your snow tower in City Creek and the one at Alta on a given day?
Well, yes, the snow tower in City Creek compared to, yeah, so we only run the snow energy balance study site up at Alta, and then we're just comparing all our modeled data to the Snowtown network. One of the stations there is in City Creek. And obviously, yes, the elevation difference between those 2 sites is quite quite big. So we don't have observed solar radiation or albedo, though, at the City Creek site.
Not measuring dust at City Creek relative to Snowbird.
Not in the field, no. We can look at the remote sensing record, kind of the pixel over City Creek, right? And look at that trend compared to the retrieval over Alta, for example. Yeah.
I'm kind of curious about, you said that the pixels were like 100 by 100 feet or meters.
Meters, yeah.
How are you parsing out what in that area is snow versus if there's any exposed rock or anything else that could be contributing to reflectance?
Yes, that is kind of built into the algorithm we're using. So we're pulling in these snow albedos, but they've already gone through kind of a filtering step. It's called spectral unmixing, where they actually look at the signal, the spectral retrieval of that pixel, and they parse out kind of what % of that is snow, right? What % of that is vegetation, what % of that is rock. And then they're essentially just taking the snow part. But mixed pixel effects is essentially what you're talking about, and it can definitely contribute to some errors. It's never going to be fully gone. Yeah.
Okay, great session. Thank you, Otto. Let's give him a round of applause.